This is about DC and AC steady state. What is steady state? If we haven't opened or we haven't closed a switch, any switch in a circuit for a long time, the circuit is in steady state. But what is a long time? How much time is a long time? You see, that depends on the circuit. In a given circuit, let's say that a certain current has that form, the expression at the bottom of the screen. We identify the exponential terms, and each one of them will give us a different tau, a different time constant. 5 times that tau, and that exponential term will be gone. In this case, that system, that circuit, has 2 time constants, half a second from the first exponential and 4 seconds for the second one. We take the longest one. We wait 5 times, 4 seconds, 20 seconds, and the circuit is back in steady state. Let's rephrase that. For this circuit, if we wait more than 20 seconds, the circuit is in steady state. Steady state, huh? DC steady state? It depends. DC steady state. If we wait for a long time after operating the switches and all sources in the circuit are DC, then we are in DC steady state. The consequence is that all currents and all voltage in the circuit will be constant. Not only that, behavior of reactive elements will be peculiar. Inductors will behave like short circuits, like wires, and capacitors will behave like open circuits. And that is that. But if we've waited a long time, we are in steady state, but all sources in the circuit are sinusoidal functions of time with the same frequency, then we say the circuit is in AC steady state. And the consequence is that all voltages and all currents in the circuit will be sinusoidal too, with the very same frequency of all the sources. And then what do we do with that? We can represent voltages and currents by a complex number. We can represent inductors and capacitors with an impedance in ohms that depends on the frequency of the sources. We need to prove all this, of course. And it begins sinusoidal voltages, sinusoidal currents, and complex numbers. The sine function. In the remainder of the course, all voltages and currents will be sinusoidal functions of time or combinations of them. In math, we've learned to describe the sine function like this. Y is A sine omega t plus theta, or perhaps A cosine omega t plus theta. Our choice, sine or cosine. Just stick with one. A sinusoidal function of time is completely defined by 3 parameters: the amplitude, the angular frequency in radians per second, and the phase shift, theta, in radians. Even though engineers will write that in degrees anyway, when you compute that expression in your calculator, make sure that you use radians and that you have translated that theta to radians. What is different between those two sinusoids, the blue and the red? They have the same frequency, they have the same shift, right? The same phase, but they have different amplitudes. That's what makes them different. And what about these two sinusoids? What makes them different? They have the same amplitude, they have the same frequency, but their phase shifts are different, right? One last shot. What is different between these two? They have different frequency, right? So each one of the 3 parameters is extremely important to the identity of the sinusoid. Without proof for now, when all sources are sinusoidal with the same frequency and switches have not operated in a long time, that is, we are in AC steady state, the circuit in AC steady state implies that all currents and all voltages are sinusoidal with the same frequency of the sources. But here's the thing. But in a circuit, because we use KVL and KCL, we need to find a way of adding and subtracting sinusoidal functions of time. We need to be able to add and subtract currents for KCL and voltages for KVL. But sinusoidal functions of times, voltages, and currents. How are we going to do that in an efficient manner? Steinmetz, however, changed the world. Charles Proteus Steinmetz solved this conundrum, and in doing so became the veritable father of the modern electrical engineering. He presented a paper, Complex Quantities and Their Use in Electrical Engineering, in July 1893 at a meeting of the American Institute of Electrical Engineering, AIEE. Steinmetz simplified the computations to a simple problem of algebra, as we shall see. So we need to add two voltages or two currents that are sinusoidal functions of time. This one and that one, they have the very same frequency. We represent them as the real part of two complex numbers that have an argument that is a function of time, this way. If we want to add those two sinusoidal functions of time, we just need to add the real parts of these two complex numbers. But we remember that when we add the real parts of two complex numbers, what we get is the real part of the sum of those two complex numbers. Let me show you graphically here. The real part of the sum is the sum of the real part of M1 and the real part of M2. So the sum of those two real parts is the real part of the sum of those two complex numbers. We can rewrite the exponentials as the product of two exponentials this way. And then we factor out e to the j omega t. Now what is in parentheses, in the inner parentheses, is just the sum of two regular complex numbers. We add them together, we get a third complex number, c exponential of j gamma. We recombine the two exponentials in the curly braces there and get the real part of that complex number, which is the sinusoidal function of time with an amplitude c and a phase shift gamma, the same frequency as the two original functions of time. And that is the plan, to find the amplitude and the phase shift of the sum of those two sinusoids. We represent each one of them with a complex number, the first one with a and an angle of alpha, and the second one with b and an argument of beta. We add them together, we get c gamma, and from c gamma we can write the function of time that is the result. That is the sum. That is the plan. We could have done the same with sines. This way, just use the imaginary part of the complex numbers and you get exactly the same result. Now, that's the plan. Represent each voltage or current that you want to add or subtract with a complex number that has the amplitude and has the phase for argument. And then add or subtract them together, and you get a complex number that is the representation of the sum or the subtraction of the two original ones. From there you get the amplitude and the phase of the result. You want our example? Sure. Let's run an example and a couple of top-up questions for you to practice. Here, tutorial time. Let's add those two sinusoids. Could be two currents or two voltages. 3 sine 300t plus 30 degrees and 4 sine 300t minus 40 degrees. Both sines, so it works. Represent the first one as a complex number this way, 330 degrees, and the second one with a complex number 4 minus 40 degrees. Excellent. By the way, you know those complex numbers have a name. Those are called phasors. P-H-A-S-O-R. Phasor. So we represent the sinusoids with phasors. Add them together. Let me use a calculator. 330 degrees and 4 negative 40 degrees. Make sure the calculator is in degrees up here. Add them together and we get the amplitude and the phase of the resulting current or resulting voltage. 576 is the amplitude and the phase is negative 10.71 degrees. Let me write that as a function of time again. This is the sum of the two original sinusoids. 5.76 sine 300t minus 10.71 degrees. And yes, we engineers, we write the phase in degrees even though we know that it should go in radians, and it will go in radians when we need to compute the value of the function of time at a given point in time. Conclusion. What we carry from this all is that voltages and currents are represented with complex numbers. This way, amplitude and phase become the absolute value in the argument of a complex number, of the phasor. Those complex numbers carry the amplitude and the phase of the original sinusoid as absolute value and the argument. Remember, amplitude and phase. Those two words will come up again in the following weeks in a different context. When a signal, which is one sinusoid or a combination of sinusoids, passes through an electronic circuit, its frequency or frequencies are not modified, but the amplitude of each sinusoid and each phase is modified by the circuit, altered by the circuit, depending on the frequency of that particular sinusoid. Such modification is given for each frequency by the frequency response of the circuit that will occupy us in the weeks to come. That is the end of that part, but we're not done. Now, let's see what happens to the phasors that represent sinusoids when we differentiate or integrate a sinusoid. Sinusoids, complex numbers, and calculus. A preamble. Check that out. The absolute value is 1, the angle is 90 degrees. Do you agree that that is I, the imaginary unit? Or in engineering, that is J, right? That is J, written in rectangular form as 0, 1. Real part 0, imaginary part 1. In polar form, 1 with 90 degrees. In exponential form, exponential of J pi over 2. Another one, what is this? You say, well, that is negative J. Sure, it is negative J. It can be written like that in rectangular mode, like this in polar form, and like this in exponential form. But one thing, negative J is equal to 1 over J. What? Yes, 1 over J is negative J. Let me show you. 1 over J, you multiply both the numerator and the denominator by negative J, and the numerator becomes 1. J times negative J, that is negative 1, that is 1. And the numerator is negative J. And QED, 1 over J is negative J. Please remember that because we will use that momentarily. Negative J is 1 over J, or 1 over J is negative J. Another preamble, multiplication in polar form. Let's take a number, the original one, 5 with 12 degrees, and we multiply that with 3, 35 degrees. What happens to 512 when we multiply that times 3, 35? Let me write them in exponential form like that. The order of the factors does not alter the product, right? So there are 4 factors there, 3 exponential, 5 exponential. Let me reorganize them like so. Multiply, and we get what happens to the original number 512 is that its absolute value was expanded by 3, and its phase was increased by 35 degrees. Or we can say that the second number, 512, was stretched 3 times the absolute value of the other factor and was rotated 35 degrees counterclockwise. That was the effect of multiplication, stretching, and rotation. Right? Correct. Now I'm asking to you, what happens when you multiply a complex number times J? 1 with 90 degrees. The amplitude doesn't get modified, but the phase gets increased by 90 degrees. Right. Keep that in mind. Stretch by 3, rotate by 35. A sinusoidal, its phasor, and a derivative. Consider a sinusoidal function of time. Could be a voltage, could be a current, will be a voltage, will be a current soon. This one, f of t, has an amplitude a, an angular frequency omega, and a phase shift alpha. It can be represented by a phasor, a alpha. Fine. Please observe I'm representing the phasor also with an uppercase letter with a little hat, a complex number. If we differentiate the original function of time, we reorganize, we make sure that we get another cosine function of time. This is what we get. The derivative of f with respect to t is omega a cosine omega t plus alpha plus 90 degrees. Check my math. And now I'm asking of you, this second sinusoid, the one that is the derivative of the original one, has an amplitude, omega a, has a phase shift, alpha plus 90 degrees. So it is another sinusoid that can be represented with a phasor, this phasor, omega a and alpha plus 90 degrees. Do you agree? Yes, you do. Now, this new phasor can be written as the product of two simpler phasors, of two simpler complex numbers, sorry. This one, omega 90 degrees and A alpha. Do you agree? Yes, you do. But the second term, A alpha, is just f, the phasor that used to represent the original function of time, f of t. And omega 90 degrees, well, that is just j omega. Right. So you see, whenever we differentiate a sinusoid in time, its phasor gets multiplied by j omega. You say, oh, I could have saved time just by saying I want to differentiate f of t, just multiply the phasor f by j omega, and that is the plan. That is the plan. Conclusion. When we differentiate a sinusoidal function of time, its phasor gets multiplied by j omega. The next slide I give without demonstration, and it's up to you, my students, to do the honors. When we integrate a sinusoidal function of time, its phasor gets divided by j omega. Right? Go. Take the time. Demonstrate it and come back. You're back, huh? Let's apply that finding to the inductor, to this equation. In the inductor, we know that if that is the current, I cosine omega t plus beta, then the voltage in the inductor will be given by L di dt, like so. And what that says is that if the current in the inductor is given by this phasor, I beta, then the voltage in the inductor will be given by this other vector, j omega Li. Agree? Of course, L times the phasor that is the derivative of the current phasor. L multiplied by j omega I, that is j omega Li. V in volts, I in amps, j omega L comes in ohms. So j omega L is what we will call the impedance in ohms of the inductor, j omega L, Z sub L. In the capacitor, we have the current, this one, the same current. And the voltage is given by this expression, 1 over C, integral of the current with respect to time. If the current was represented by a phasor this way, we know that if we divide that phasor by j omega and divide that by C, we get the phasor for voltage, right? This way. That is a phasor for voltage in the capacitor if we know the phasor for current in the capacitor. But now, you remember that 1 over j is what? I don't hear you. Negative j. Negative j. There you go. So, amps on the far right, volts on the far left, negative j1 over omega c have to come in ohms. And that is the impedance in ohms of the capacitor. Negative j, 1 over omega c. Let's summarize that. Represent voltage and currents with phasors, and represent inductors with their impedances j omega L, capacitors with their impedances negative j1 over omega c, and the resistors, they don't change. They are resistors. If you do that, we have Ohm's law again. The phasor for voltage is the phasor for current multiplied by the impedance of the element or combination of elements. Now, if we have the phasor for voltage. This is a retake. The phasor for voltage is the phasor for current multiplied by the complex impedance of the element or elements in the branch. Summarizing, we have Ohm's law again. We have series and parallel simplification, delta, to and from Y conversions, Thevenin equivalence, maximum power transfer. We have M&A. We can use everything that we've learned previously to analyze circuits in DC steady state, also in AC steady state. What is the catch? That now voltages and currents are represented with phasors, complex numbers, and the impedances are complex numbers as well. The rest is business as usual. Let's compare the phasors impedances and the Laplace impedances. Check this out. Those are the impedances when we use phasors. For the inductor, J omega L. For the capacitor, 1 over J omega C. You say negative J? Oh yeah, sure, negative J 1 over omega C. But let me write it like this right now because it's convenient. 1 over J omega C. And the resistor is a resistor. Do you remember the impedances in the Laplace domain? Of course you do. The inductor, SL. The capacitor, 1 over SC. And the resistor is just R. You say, wait a second. So S is sigma plus J omega, right? Yeah, that's what the complex frequency in the Laplace domain is all about. If sigma is 0, then S becomes J omega, and the impedances are the same impedances that we just found for phasors. Neat, huh? Now, what is the plan? The plan is, in a circuit in AC steady state, we represent every source with phasors, both independent current source and independent voltage sources. The dependent sources, we leave them alone. And then represent every inductor and every capacitor with their impedances. Inductors, J omega L, capacitors, negative J 1 over omega C. By the way, omega who? When I say the impedance of the inductor is J omega L, the impedance of the capacitor is negative J 1 over omega C. What omega? The omega of the sources, the one and only. Remember, only one frequency in this circuit. And then we solve the circuit for any voltage or current that we are interested in, and what we get is the phasor of that voltage or of that current. From that phasor, we can write the current or voltage as a function of time and then evaluate that at a particular point in time. Let's say, find me that voltage or find me that current at t equals 0, which is something that I ask of you often in exams. Tutorial time, we have that circuit. The circuit has 4 resistors and 3 reactive elements and 2 sinusoidal sources. However, the sinusoidal sources are nullified at t equals 0. Observe the inverted Heaviside steps on each one of them. They become 0 after t equals 0, so the current source becomes an open circuit and the voltage source becomes a short circuit. But that is for another question, not for this one. We worry about what happens before t equals 0, when the circuit is in AC steady state. The question is, find the current in each one of the inductors at t equals 0 and the voltage in the capacitor at t equals 0. And that is all for today, my students. Thank you very much for joining, and I hope to meet with you again in our next video.